presumably our predecessors also used some batteries, right?
There ought to be two, so you can toggle, but I don't know unless the others go and walk about somewhere. So that ought to have come on. It's possible that this isn't recording, in which case, too bad, basically. Nothing much else that we can do. I mean, I think that ought to also come on. Yeah, not recording. I don't know why. Is there any way to make it record?
You push the pause button.
I'm reluctant to do that.
It's ignoring you anyway.
Oh well, let's go.
Okay.
Hello everybody, welcome to comp5348. This here is Paul Greenfield, the person whose name is on the slide and is going to be your lecturer for today. My name is Alan Fekete. Some of you know me, some of you may not. I'm the unit coordinator. I'm going to start by going through a collection of administrative material, which I hope will just clarify things. And I should say that these lectures are supposed to be recorded, but it appears at least that the recording is not happening today. I'll try and see why or what's going on, but in the meantime, you know, maybe taking notes would be a good idea, though the slides have been posted and I hope that you've already seen them on the Canvas site. Can I just get a quick show of hands? Who has seen the slides on Canvas? Okay, so some of you, the ones who haven't, you need to learn where to look. If you go to the Modules tab of the Canvas site for this unit, you should see today's slides, and each week the slides for that week should be there, as well as tutorial instructions and so on. Okay, so you know, people who are here at least know where and when the lecture is taking place. Labs follow immediately after the lecture, so on Wednesday nights at the end of the 2-hour lecture slot, we all go over to the School of Computer Science labs. For those of you who were here in previous years, that was what used to be called the School of IT labs. The school has been renamed, and so therefore so have the labs. Your timetable will tell you which of the labs you're in. They're all running in parallel, so there's only one time slot for labs. And of course, it's crucial to be paying attention always to Canvas. So, as I mentioned, I am the coordinator for this unit. So, my name and email are there, Alan Fekete. You're welcome to call me Alan. I don't insist on any level of formality. The way it works is we have here somebody who knows about the topic, namely enterprise scale software architecture. Paul has many decades now of excellent practical experience in the field. He has consulted and designed and implemented and all of those things. He worked at CSIRO for many years. We collaborated on research related to this topic. So Paul is the person you should ask if you want to know about any of the actual facts, the content, what an assignment question means, or anything like that. On the other hand, Paul is not an employee of the University of Sydney in the full-time sense, and therefore he really does not want to be bothered by the arcane bureaucracy of the university. That's what they pay me for. And therefore, if there are any issues at all which run up against the university's structures, I'm the person to come and see. If you are having difficulty getting a request for an extension approved, if you are having difficulty with getting access to the Canvas site, all of those things, I am the person to see about that. In addition, because I'm sort of the ultimate paperwork authority, if you have any issues with a tutor or whatever, again, you can come and see me. If you have any difficulties in group work later in the semester, I'm the person to bother. Okay, so if it's a question of actual technical knowledge, Paul here is the person who knows. If it's a question of dealing with the university, I'm the one who has to suffer through it. Okay, does everybody understand when you talk to Paul and when you talk to me? Great.
And
Okay.
if they come to the wrong person, they'll be redirected anyway.
Indeed. We have 3 excellent tutors for the 3 different rooms. They're all people who have taken earlier versions of this class and done very well and have plenty of industry experience that's relevant, and so they're going to be giving the tutorials for you. What is this class about? The most important thing for you to understand is that this class will not leave you ready to be a software architect. Software architect is not an entry-level position that you get into after you finish your master's or your engineering honours or your computing 4th year studies. Software architect is something you get into after you have been pickled in the industry with lots of experience and learnt a lot of things in the school of hard knocks. On the other hand, when you go out into the industry as a new graduate, you will probably work with a software architect. There will be somebody around who has had those years of experience. And what we want is that you can work effectively with that person, that you know what they're trying to do, you know enough about the language to talk to them, to have a conversation with them about what they want and why they're saying what they're saying. That if you disagree with them, you're in a position to make your arguments in a language that can communicate with them. In addition, we know that quite a number of students go out into consultancy-style roles in which you're going to have to essentially go and write reports and write, evaluations. Somebody will say, this is our proposed architecture. We're hiring a consultancy firm who will send out some new graduate to write an analysis of it. You may well end up in that role. We want you to have some skills to do that. There's also a bunch of knowledge. So in this unit, as you see, as you go through, there are lectures which are very much understanding the conceptual framework of software architecture. Paul will be teaching you about the technologies and the choices that they imply and how that relates to the quality attributes of the systems that are being designed. But in addition, there is a bunch of quite concrete technical skills which a software architect needs to have in their kit, and any developer ought to have in their kit. I have had students come back, after they've been in the industry for a year or two and tell me from previous versions of this class, that was immensely useful. Or even, they asked me that in my job interview. So that concrete stuff, you'll recognise it when you see it. It's the stuff where the labs are paper-based, you do calculations and estimates and so on. It's very much the stuff that is the focus of your written assignments in this unit, and there are exam questions on it. So very solid technical knowledge, bit mathematical perhaps in its flavour, but very, very useful. That's another part of this unit. Finally, like many units in our curriculum, there are what are sometimes called the soft skills, except that they're really, really hard to master. Working in teams, working with people of different backgrounds, managing yourself and your groups. And I'll talk a bit more about that, but that is also one of the things that happens in this subject. Okay, so that's what you should be hoping to get out of this subject. Should you do the subject at all? So, firstly, this is a subject, specialist subject in the Masters, a fourth year or honours level subject for undergraduates. That means we have fairly high technical expectations already. This subject expects that you come in comfortable with the concepts of object orientation and actually able to use it, able to write code, look at code, debug code. If you don't have that technical skill, this is not the subject for you, and we strongly suggest that you go somewhere else. In this subject, the focus will actually be on using C#, but we expect that if you've spent your last several years working in Java, the transition will be pretty straightforward. If you're not able to make that sort of transition from one language to a very similar language with the same concepts but slightly different syntax and different tools, again, this is not the subject for you. Okay, so this basically says the same thing, that you need to have OO programming competence. Now, if you are struggling to look at some code and work out where the classes are, what the methods are, how the calls are flowing back and forth, why various arguments are where they are, don't do this subject. We also do expect some exposure to what's the sort of data modeling side of the world. You might have had that from a database class. You might have had that from an object-oriented design class. But you're comfortable with the idea of there's stuff in the world and you can recognize what the classes are and that they'll show up as code, and you'll have some understanding at least of what it means for one class to have attributes which come from another class and so on. And finally, you should have had some experience in software development, because the processes that you need to go through, actually understanding requirements, developing tests and so on, is stuff that you will need to do in this subject. So, if you are dubious, you can talk to Paul at the end of the lecture and describe what you know, and he can give you some pointers as to whether this is the right subject for you. Administratively, okay. Maybe I should ask at this point, who here is in their first semester at the University of Sydney? That is, you have not previously taken subjects at this university. Okay, so some of our postgrad students may be new here. Okay. This university is a large bureaucratic institution. It is committed to research and scholarship and learning, but it is also a big administrative machine. That means you need to know policy, you need to get your paperwork right, you need to follow the rules. And so you should know what those rules are. In today's lecture, I'm going to be telling you the most important ones, but as they say, ignorance of the law is no excuse. Okay? If you are supposed to have done something with your enrolment and you haven't done it, you will suffer, and there's not much we can do to salvage you. So make sure you know how the place works. In addition, we want you to prepare for the tutorials. Obviously, you probably haven't read today's tutorial very closely yet, but in general, the goal is that you should actually have looked at the tutorial before you come to class. It probably won't make a huge amount of sense to you
That's true.
when you look at it before the lecture, but if you know what the tutorial is about, you can connect bits of the lecture to the tasks you're going to do in a much better way. So please look at the tutorials. We'll try to get them up every week, at least a day in advance. This is not a subject where you can show up in week 12 and say, oh, I guess I should start studying. This is a subject which has a lot of stuff. It builds. So the technologies that you study in the tutorials this week, you will be using next week and the week after and the week after. The stuff from week 2, you'll be using in weeks 3 and 4 and 5. If you fall behind, you have great difficulty. So don't fall behind. I mean, look, we all know sometimes stuff happens and there is a week when you just don't get work done. But catch up the next week. Don't leave it. And if there is an issue, come and talk to us. I'll also point out the fact that you are here on Wednesday evenings from 6 till 9, that's 3 hours of time. Spending those 3 hours on this subject is not enough. The ideas are complicated. You need to do work out of class time. Our expectation is that you should spend at least 6 hours a week on average, in addition to the 3 hours you're here on a Wednesday night. Those 6 hours involve working on your assignments, but they also involve thinking back over the previous tutorial, finishing off anything you didn't get done in class, trying things out, making sure that you've got the skills under your fingers. Here's the course outline. You'll find it on CUSP. There's a link to CUSP from the Canvas site. The stuff about when the assessments are due ought not to change. The stuff about what's actually done in every week could change depending on what happens. So don't rely too much on that. The way you know what's happening in every week is the lecture slides go up and the tutorial instructions go up. Okay? But the assessment dates are crucial. So there's an initial assessment due in week 3, and that's a preliminary version, and it's actually then due for real in week 6. There are paper-based assignments due in week 7 and week 11, and there is the group project due in week 12, and I'll talk in a lot more detail about those in the next slide. So, sorry, that's a mistake. This isn't A0, this is actually A, task A, part 1 and part 2. I'd just like to stress, this is not an assessment in the sense that it's there to be a major component of your marks. This is to get you ready with the practical skills so that you can take a fair role when you get to the group project, which will start afterwards. So this involves looking at the software, which is the basis for the group project, so you know what goes on in that software, and it involves doing some stuff with it so you make sure you get your C# skills and your IDE skills and all of that up to speed so that you are ready. The group project then carries on from that, and that is the one which actually is the place where the real content of this unit takes place. That's the one where you have the sort of thing that software architects typically have to deal with. They have bits of systems which are already existing, and they have to extend it, build it, make something to achieve certain goals, which are not just functional goals, but also quality goals, various sorts, non-functional requirements. And so there's the actual coding work there, which is not a lot of code to write, but it's a lot of understanding and a lot of thinking about what is the right way to put these bits together. And you have to evaluate it. You have to actually say why you chose one way rather than another way, and what the implications are. So that group project is the major place where you demonstrate the skills that this unit is giving you. In addition, there are 2 paper-based assignments, Assignment 1 and Assignment 2, which are the places where you practice those especially calculational and estimation skills that I spoke about, and they are also really solid preparation for similar questions on the exam. And then there's a final exam, and I'd just like to remind people who've been here before and tell people who are new, it's a policy in the School of Computer Science, another typo on the slides, that you have to get at least 40% of the marks that are available on the final exam. Doesn't matter how well you do in the prac work, if you don't get at least 40 out of 100 on the final exam, you will not pass. That's a general policy, you'll see it in CUSP, and it applies in this subject. What about late work? So the university has a new policy regarding late work. So what we've said is that for assignment A, task A, you cannot hand it in late. Because that's the one which is getting you ready to go into the group project, giving an extension doesn't make any sense because the group project's underway. Okay? If for some reason you can't hand work in, then we will find other things to use as the basis for the assessment, but you really need those skills at that time. For the other parts of the course, we're following the university's standard model, which says unless you have special consideration, there is a standard penalty for late work. 5% of the available marks are lost every day late, and that's calendar day, right? So Saturday is a day, Sunday is a day, every day is a day, and your mark will drop 5% of what's available every day. But after 10 calendar days, you will receive 0. If it's more than 10 calendar days late, it goes to 0. Okay? Any questions about that? It's a new policy, so some of you may not have experienced it before, but questions? Okay. That's what happens if your work is late without special consideration. The university has a bureaucratic process for cases where your work has been affected and you might need an extension because of sickness, because of events that happen to you, what the university calls misadventure. You know, that includes things like you're kicked out of your apartment and you have to spend a lot of time looking for a new place to live, or you're involved in a court case. It's not just being sick, but being sick is the most common form. The university has procedures for this. There's a website that you should become very familiar with, which explains to you how to do that. If you're sick and you go to see a doctor, there is a special university form. Don't let the doctor just give you a standard medical certificate. There's a special university form they need to use. You then go online, hand in, you scan those documents and fill in forms. Couple of points to note, you only have a very short window from the deadline of the work to get those forms in. If your illness or whatever prevents you getting the form in, there is then another process to apply, but you have to explain why you didn't get it in time. The other thing is when you apply for special consideration, make sure you use the correct name for the assignment as it is found in CUSP. So if the assignment is called Prac Task A, call it Prac Task A. Don't call it Assignment A, don't call it Assignment A0 the way I did. Call it exactly what it's called in CUSP. Because these documents are processed by administrative people who don't know anything about the subject. They don't come to me. The administrative people just look at what, you said the due date was this, they look in CUSP, doesn't match, they just reject the application. And I can't do anything. The other thing to say is, if you are being affected by illness, let me know. That's separate from the official paperwork, because the paperwork doesn't come to me. Let me know immediately, and I can try and work with you, both to guide you through the process, but also so that we know and can adjust as necessary. Again, people who are new, I just want to stress the importance of academic integrity. We know that there are services where people will write assignments for students. We know that there are students who will pass their assignments around for other students to copy and so on. Don't do it. It really isn't worth it, particularly in a subject like this, where fundamentally the exam will catch you anyway. But in any case, the penalties are very severe and the gain is not great. So, it's also just not the right thing to do. Okay, here are a few questions just to make sure that you know about. If any of these don't sort of automatically tingle your brain with what to do, come and talk to me afterwards. Okay, work health and safety. You're going to be working in computer labs in the School of Computer Science. Computer labs are not as dangerous as, say, heavy engineering labs, but there are still things you need to do to keep yourself and everybody else safe. One of the most important is to make sure that there aren't things left lying around to interfere with people's movement, whether that's bags on the floor or power cords. So don't move the equipment around. Don't leave your bags or mess around. Don't bring food or drink near the machines. That's not so much only for safety, but that's also because it's remarkable how much damage a keyboard can take from a can of drink. Okay? The university has a lot of emergency material that you can watch. There's a URL there that you can go and follow. Once you're in the labs, though, the most important thing is to know that if there is an emergency evacuation, you head, so your labs are around here, you head out of the building and over to the area in Cadigal Green, which is where people will be assembling. Okay? Do not stay around in the lab. Yes?
Just currently under construction.
So there is a big construction site here, but so this is the Seymour Centre. So actually, yes, you're right. The area is actually, I think, just over here, but the route is still the same. You go up this way, past the side of the Seymour Centre to Cadigal Green. Cadigal Green, I think, is actually over here. So, thank you. Need to update this slide. Okay. If somebody becomes sick or injured in the lab, if you're not sure that it's okay, call the ambulance. Then there's also calling security afterwards. But don't stand around thinking, should I do something? Call an ambulance first to be on, to make sure that nothing serious happens. Okay, there are people that you can report incidents to. So typically it's Cecilia, 93516060 is her number. But hopefully that all won't arise during these labs. Also, just want to stress that the university has a lot of support available for students in all sorts of categories. Particularly, I'll draw your attention to disability services, who can provide help with all sorts of conditions that are more lasting than simply something that affects one assignment. So disability services deal with things that are larger than just a particular piece of work. They include physical conditions, social conditions, mental conditions, all sorts. And they have a lot of support available, so please make use of them. Another slide from them. Okay, there's also learning support for students of particular sorts. If you're an undergraduate, the SRC. If you're a postgraduate, SUPRA. Your representative organisations, and they can help you. Okay, there's a book which is good to consult, and there's a copy, an online copy available in the library, so you can look at it anytime you like, and that will help flesh out or give you a second perspective on the things that Paul will be talking about in lecture. Some of the particular weeks have other books, which we'll be referring to again when we get to those weeks. And finally, there's some very good online material from Microsoft about how applications are constructed that fit the pattern of the one you're going to be looking at. So the particularly layered architecture. Paul will be talking about that later today. Okay, as I said, we're working in C#. The software is Visual Studio and a bunch of other technologies which fit together with that. So basically, this semester, we're in Microsoft land. I know many of you are experienced in Java, so it will be a little like travelling to another country, but it's not that strange a country, and learning to adapt to this is one of the key outcomes that we expect. It was a key skill we expect you to have in this class. Finally, a couple of very general slides of advice. Many of you have seen these slides in my lectures over and over again, but still worth paying attention to. The assessment will align closely with the learning outcomes that are listed in the unit of study outline and on CUSP. Okay? We will make sure that the exam enables us to say whether you have achieved those outcomes. So pay attention to those outcomes. Keep saying, okay, this outcome, what have I learned that will enable me to demonstrate that outcome? What sort of question would I expect to be asked to connect to that outcome? Time management is very important in this subject. We have quite a lot of assessment, both the written assignments, which do require more time. They're not things you'll knock off in the evening before they're due. So plan. Use this class as an opportunity to get to know a wider variety of students. This class has a mixture of master's students and final year undergraduate students. Don't just stick within your own cohort, mix across cohorts. That's valuable for both of you. You know, one of the great things about Sydney University is it helps you widen your social network. This class gives you an excellent opportunity to do that, so make use of it. Have fun. This is a class where you will learn some amazingly useful and powerful things from somebody who really knows how the industry works and has seen it through many cycles of boom and bust and hype and technology change, and can give you very valuable insights. Really learn from it and enjoy the learning. Finally, there's a group project, as I said. Who here has hated a group project that they've been involved in? Come on.
That's good.
Seriously?
Question. How many
Okay.
really enjoyed them?
Okay, who has done a group project? Okay. All the people who've done it and enjoyed it. Okay, well, maybe it happens. What we have seen in the past is that there are often a lot of difficulties in the group projects. Key things that you need to understand is the group project, you all get the same mark. We can help with clashes, disagreements, but only if we're told early. It really does no good at all to send me an email the week the assignment is due to say so-and-so hasn't contributed. It's too late then. What I need is an email much earlier, which means that in your group organisation, you need to set things up so you set deadlines for one another and watch if those deadlines are missed and do something about it. My suggestion is typically have a deadline every week, and if something is missed that week, get in touch with the person, arrange a fix-up the following week. If you can't reach the person at all, or if the following week they haven't fixed it, immediately get to me. And that should give me time enough to deal with stuff. Otherwise, you'll have a situation where each person has been contributing week by week, and you can manage. Okay? So, at that, I think it's time for me to ask if you have any administrative questions of me. Yes?
So this question is, how many members who form a group?
The groups are typically 4, I think. Four or
3, it seemed.
3?
3.
It's either 3 or 4. Well, that will be in the instructions. So the groups will only form when that work starts, which is basically at the end of your task A. So at the end of task A, there'll be a lab where groups get formed in that lab.
Are those tutorials week?
Yes, tutorials start today. So at the end of today's lecture, Paul will talk about today's tutorial. The instructions are in fact already up on the Canvas site, but we realise that you haven't seen them yet. Paul will be talking through the tutorial. I mean, today it's really a lab more than a tutorial. So some weeks it's more tutorial-like, where you work on problems on paper, but most weeks it will be working with the technology on the computer and more like a lab. Other questions? Yes?
I noticed that this choice to use the community edition for the Visual Studio, right? Is that available for this course?
Okay, so the Visual Studio, so my understanding is that the university's arrangement with Microsoft means that students have access to a bunch of stuff. I believe it includes...
Well, there's two
Visual
questions
Studio.
there. So if you're interested in just Visual Studio, there's a community edition which is free. You can just run it. And if you want the professional editions, which don't provide much more for this type of purpose, then the university has agreements where you can sign up to DreamSpark, is it these days? The names change frequently, but you can download some, as a student, you can get copies of software.
So stuff you get for that purpose can't be used outside your student existence. So, you know, don't go and do a startup on it. But for the purposes of this class, as a University of Sydney student, you have access to a lot of Microsoft stuff. Other questions? Sorry, using Windows.
Yes. Yes.
Okay, so the
Because that's what Visual Studio runs on.
the lab machines are dual boot, and for this subject you'll be using them under Windows. Okay? Now, if you want to do work on your own machines rather than, you know, connecting in or whatever, those are things you need to deal with. I mean, there are lots of possibilities for you to get platforms which allow you to run Windows stuff within, you know, a virtual environment on a machine. So you don't have to turn your whole machine into a Windows machine, but that's stuff that you can deal with if you want to be working on your machine. The lab work is done with the machines in the Windows side.
Instead of using Visual Studio, is it alright if we use another one, like a writer?
So if you use a different IDE,
No, you'll find that's just far too hard. You won't be able to follow the step-by-step instructions because it'll be all different.
Yeah. Right.
okay.
So, the community edition or the Mac version of Visual Studio might help.
So
Still
so there's also VS Code, which is a different animal altogether, and that runs on lots of things. It probably won't do the job for visual here because of the integration and all the frameworks it needs. Because it's not just Visual Studio it's using, it's the .NET frameworks it's using to provide the frameworks that code is written into.
more than the code.
Yeah. So it's more than just an IDE, it's also the frameworks, which are the examples you're all looking at. And then there's also this new animal which is called Visual Studio for Mac, which is another animal altogether. And there's no native .NET framework for Mac. I can't see how that would work either.
They say when you install, okay, I'm installing .NET Core, so I was assuming that it might work, but maybe not, I guess.
That would be an interesting experiment sometime to port all this stuff which is currently written in .NET framework to .NET Core. And that is probably technically possible to do without too much trouble. Yeah, but today,
I mean, this subject is a Microsoft World subject.
that's
Right.
what the prac is based on.
The track is in that ecosystem. So yes, even if you are a Java person from all your previous study, you're travelling into a new world. Okay, so I will hand over to Paul for then. Let's just exit this and get the other lecture slides up. There we go.
It's
So,
lovely.
Paul, over to you. You've got my email, everybody. Email me if there are any administrative questions, but remember, if it's anything about the actual technology, he's the person. See you.
while I'm trying to plug myself in and find that not having talked for that 3/4 of an hour, I was talking, my voice doesn't want to work anymore. So at some stage you actually need a break. So we can either go for 15 minutes, have a 5-10 minute break and then come back in, or you can have a break now. It's your call. And does this work? Oh, it just works. Okay, so some history. Once upon a time, two people, Ian Gordon, whose name you saw in that book, and me, wrote a couple of courses for this place. And then Ian did what Ian normally does, which is disappear to the other side of the world, and that course got morphed into what is effectively this course. And then I taught it for a number of years, and then I handed it over to Matt, and now it's come back to me again. So some of the slides here that I haven't seen for a few years, because I've been doing other things for a few years, oh, I remember those slides, I wrote those ones. So this is a course which has had quite an evolutionary history like everything else does, but deep down is a course that Ian and I wrote a long time ago, and for different purposes and with different goals. All these people listed on the bottom there have all contributed to this course at some period of time. I'll ignore that boring slide. The person who has run this course for most of the last few years, not last year, but few years before that, and was tutor for me prior to that, has structured most of the lectures so that there are a number of topics, and then there is a small bit of screenshot working through things, which is a bit like the tutorial-y stuff, but it just helps with some hands-on examples. So today, because we're starting quite late, we may not get to do much of that mini prac lecture 1, but they're really just screenshots, and they're doing what you'll be doing in the prac tonight. So if we don't get around to that, that's fine. The core things in today's lecture are talking about what software architecture means, what a software architect does, and the emphasis on non-functional requirements. The functional requirements are, when I push this button, I want this type of thing to happen. Non-functional requirements aren't about that at all. They're about, how do you guarantee the system is going to actually work? How do you guarantee it's going to work in this, despite failures? How do you it's going to work when all of a sudden there are more people using it than you expected? How do you cope with a power failure? How do you cope with, how do you design it so that you're working with people on the other side of the world? What happens if their network links are slow? They're all non-functional requirements. This is between a system which is functionally correct and one that works really well. You've probably all used systems where, well, functionally it sort of works, but I can't stand to use it. You know, or I spent 10 minutes doing this, and then it dropped me and lost everything I just did. They're non-functional requirements. How do you get high availability, high performance, robustness? And they're the type of things that architects, amongst other things, are concerned with. And the question of why it's called architecture, let me get back a slide. So I suppose we use the word architecture because we use the word engineering for writing software. And the relationship between, say, civil engineering, building, and an architect, a building architect, is exactly the same one. The building architect is the one who says, this is how the whole thing is going to hang together. This is the vision for the entire system, and what the core pieces of that design really are, and then you'll hand off other pieces of it, other detailed pieces. But the architect is doing the high level stuff there, making the big decisions. And often I find you spend all this time thinking something through, and then someone says, well, that's obvious. You think, yes, but there are another dozen ways I could have done it. which I thought about and discarded. And the fact that you think this is an obvious solution is probably a very good outcome, but it may not be obvious when you first start. So the architect is doing that high level structure and thinking about the big questions, and then there are other people who are doing detailed designs, but within the framework set up by the architect. Obviously, there are IT systems everywhere. The world runs on them. The number of, I'm using this phrase, the number of greenfield solutions, which has nothing to do with my name, but meaning greenfield solutions, is rare. You almost never get given a blank sheet of paper saying, here's a budget of $10 million and a blank sheet of paper, we want a system to do blah. Go ahead and do that. Really rare. It's rare because it's incredibly high risk and incredibly expensive. What instead is we want to add this functionality to our existing system. And by the way, the existing system's got to keep on running, and our customers have to continue operating on the system all the way through, and you almost never have a blank sheet of paper. I suppose the only people who do are either brave. Any of you work for Combank? No? Good. Sometimes we get people from those places. A few years ago, about 10 or so years ago, Combank had a customer management system and they rebuilt it from scratch. They had a system which was clunky and probably running on an IBM mainframe, and they rebuilt it using .NET technologies and rolled it out, and it was an incredibly good success for those people, and that particular part of the company did very well, but it's incredibly high risk. There'd been a decade before that, Westpac had decided that they were going to go and do a brand new banking system from scratch in modular COBOL because they were those type of people. And after having spent a lot of millions of dollars, it all got scrapped. Blank sheet of paper, and it failed totally. So the reasons why people are wary of doing blank sheets of paper designs. And if you're looking at someone like Amazon, I assume Amazon have done blank sheet of paper designs a few times because they started off doing this and then the business grew, and there's some very clever people architecting their system on the way through as well so they can cope with radical change and growth. But at some point they've got an architecture and have stuck with it ever since. Perhaps the first 5 years they did 3 or 4 systems, and then they learnt from that one, built a new one, rolled everything across until they got to a point where they say, okay, now this is how our system is built. We've now spent the money on building infrastructure, and now we've built it, by the way, we can sell it to other people. And then you get AWS coming out of the technologies they built and the architectures they built to serve their own needs. But those type of customers are very rare. Instead, generally an enterprise IT system is going to be this incredible mess, is a good word for it. Legacy is sometimes used as a pejorative term, but it just means stuff which is not currently active being developed. It's the stuff which is working, making money for us, doing useful things, and some architect or some salesman persuaded the company to go down this path 10 years ago, 15 years ago, and it's working. If you want to replace it, you've got to persuade management that it's worth the $20 million to replace a perfectly good functional system. Well, why would you do that? So what you're instead doing is evolving and adapting and taking this piece, pulling it out, plugging something else in to do it, which will either be better or provide new functionality you can't otherwise do. But evolution, adaptation is the rule. Lots of glue, lots of heterogeneity. A mess. Let me look at the next slide. This is a slide that I first put in this deck, and one of the people I was working with who ended up going from Cyro, where I was working with her, to Microsoft as an architectural consultant. And early on in her days, she gave me this slide, and it was a system she was working on. I think it's a bit, possibly a bit banky, possibly a bit governmenty, looking at the names of things, but this was a real customer system that she got called in to do some consulting on. It's got almost everything you can think of in it. It's got, I think it might be banky because it's got Hogan in there. It's got a old IBM database. It's got DB2. It's got a really ancient database called Universe. It's got Hogan, which is bank software. It's got multiple types of middleware. It's got it's got web servers. It's got 2 or 3 different types of web servers in it. And it's just because that's what happened. Perhaps there was a different branch of the organisation wanted to do a system and then it needed to be plumbed into the rest of it. That's just practicality. Thousands of applications, terabytes of data, millions of lines of code, some old, some new, some will be replaced sometime. That's the reality. If you're doing that again from scratch, you wouldn't necessarily have as many lines. You might have a nice clean structure, nice clean ways of getting from place to place. You'd rewrite all these millions of lines of code, but you're not going to get the budget to do that. And we've talked about architecture, but of course it's also a layered thing. You might have an overall architecture, and now we've got a lump over here which does this function. That will have its own architecture. Some of the constraints and rules of the overall system may apply to that, or it may just have evolved differently and there's got to be some type of glue plumbing to get it in, but the individual components will have their own architecture as well as an overall architecture. The types of things we talk about in architecture, we want to know how the software is composed, what are the components in it, so how do we make up the pieces, how do they communicate with each other, and how do they pass messages, under what circumstances do this, there are rules about that, and how are the bits physically distributed. So if I go and say, well, if we're going to do this type of stuff and move it to the cloud, then, oh good, we've got cloud-based architecture. Well, perhaps that's impacting on that allocation question. Perhaps it's impacting on the behaviour because we're now moving something to a set of infrastructure. As part of the infrastructure, there are rules on how you communicate with the things in the infrastructure. So that might to feed back to here, but it may not impact on that, how the application is structured question, apart from the fact we've now taken these bits from on-premises and moved them to someone else's computer, perhaps a virtual one. Some definitions. It's always nice to have an ANSI definition for something. Architecture is the fundamental organisation of a system, embodying its components, their relationships to each other and the environment, and the principles governing its design and evolution. And the principles are important because they're why you say that's a good way of doing that, that's a terrible way of doing that, because there are rules and they are part of the architecture. The SEI, Software Engineering Institute, which is where Ian ended up on for part of his journey, the Software Engineering Institute at they're in Philadelphia, they're in Pennsylvania, they're in Carnegie Mellon. Architecture of a program or system is the structures or structure of the system, comprising the software elements, the externally visible properties of the elements, and the relationships between them. Again, we're seeing the idea of of composition and relationships coming through there. And there's another one, structural issues again, protocols. This is going into a bit more detail on some of the non-functional requirements. How do the components communicate? How do they synchronize with each other? How do they access data? How do you pass data around between components? How do you assign functionality? How do you distribute the physical lumps? How do you handle scaling and performance requirements? And how did you select amongst multiple design alternatives? The architecture defines the structure of a system. We've got a system, 20 million lines of code. Is 20 million lines of code a lot of code? A million lines of code a lot of code? What's the biggest program you work with? 100 lines of code? A million lines of code? If you have a million, so the biggest program I've been responsible for being architect of was about 500,000 lines of code. And with a million lines of code, first of all, you can't write it all yourself. It's too much. It's you probably, as the person who's in charge of it, don't understand what most of the lines of code do, because you can't understand a million lines of code. That million lines of code has to be incredibly well structured. It's got to be structured so that you can give one person, say, here, go and write this. This is how this bit works, how it links in with everything else, how to test it. Someone's got to make those decisions. It might be an architect, it might be someone the architect has given the plans to, but you've got to decompose things. You can't, a million lines of code is not going to be one method. It's going to be highly structured into pieces which are manageable and testable. How you do that decomposition is an architectural question. So we had the million lines of code. How do we chunk it into meaningful components? And that's questions of layering, questions of partitioning functionality come into there. So how do we distribute the function amongst those components? How do we make those components so they're going to be usable? The interfaces that the components export, how do we talk to a component? How do we know how to talk to it? How is its capabilities, how are they exposed to the world? So what can a component do? How do we ask it to do something for us? What are its expectations? There are protocol level questions there. Protocol? You know what protocol means? Protocols are the sets of rules you use for communication. I can ask you to do this, but to do that, I have to send you a request like this. You will send me a response back like this, this, or this. If I get this type of response, then I can reply to you with this type of request. That's a protocol. And there are normally multiple layers of protocols. You know, you've all heard of things like TCP/IP, which is a protocol. But that's a network level protocol. But every application, again, we're dealing with protocols. Even if you don't define them formally, you probably should, because it's a major part of the design to understand what the message flow, what the communication flow is. If you're on an e-commerce site and you're buying something, there's a protocol to do with how that session works. I click on this, I go to the cart. So there's a protocol where it says, in order to buy things, you need to have this backwards and forwards between the client and the system about browsing things, moving things from here to here, and then, so there are protocols everywhere, and it's a good idea to try to formalise them so you know what the rules are. Because some program, when you say, okay, I want to pay for everything now, it's going to say, you haven't ordered anything, how can you pay for it? So there's a protocol which says you must put things in a shopping cart before you can pay for them. How do you put things in shopping carts? Put things in shopping carts by finding an item number and a quantity and transferring it across to here by calling that system to do this. They're protocol questions. Some of the papers that Alan and I did were we're interested in just these application protocol questions and proving correctness of application protocols, because protocol design is hard, but you've got to get it correct, because otherwise what you effectively have are little state machines. State machine? Computer doesn't know about state machines. So all the components in your system have a state, and you move from state to state by receiving a request and responding to it. So there's all these little state machines, and the state machines communicate and move between states by exchanging requests and responses through a protocol. And if you don't understand what your protocol is, you don't understand the sets of rules the system is working by. So component interfaces, that's part of the protocol question. Communications, how do we communicate? What's the protocol? How do we ask something to do something? How do we tell if it's done it? How do we get messages back? At both the application protocol level and the infrastructure protocol level. And component responsibilities, both functional and non-functional. When you call a component to do something for you, what are you actually expecting it to do? And how do you know it's done it? And what happens if something goes wrong? Yeah?
Probably a silly question, but HTTP is a protocol, but on top of that, when the SOAP runs, that defines a set of rules.
Yes.
So can that be a protocol?
Yep. You normally have protocol on top of protocol on top of protocol.
Oh, right.
But at the very top level, you have an application level protocol, which you may not even realise you actually have. So, but if you think about, if we were building, we'll take an e-commerce site. I'm going to build an e-commerce site, and I've got these components that people can call from the web. They pass me a message using something, using a SOAP call or a REST call, but I'm defining that before you can send this message, I must be in this state, therefore I must have received that message from you before that. And when I get this message from you, I will respond with this or this. And they're protocols. Now, so in that case, we might be, say, doing REST calls, which are HTTP messages. HTTP is a protocol. So we've got an application level protocol in terms of what messages we're passing backwards and forwards between the components. That's sitting on top of HTTP, which is a protocol. HTTP is sitting on top of TCP, IP, or something, and so multiple layers of protocol. And just the way the world normally is. There was a protocol called OSI. You heard of OSI? It got beaten by TCP/IP, which is good and bad. There are some good things about OSI. And it defined a 7-layer stack, which is the only thing that OSI is useful these days is people know about the 7-layer stack, which means they don't normally know what it means, they just know there were 7 layers. So OSI had a 7-layer stack. At the bottom layer we have the lowest layer of networking protocol, and then you have layer on top of that, and the very top layer had application layer. So they were expecting you may well have 7 layers of protocol. And some of them do things like, well, TCP, you've got a reliable transport layer there. And it's built on top of an unreliable transport layer. So the reliable transport layers, they're saying, how do I build a reliable layer from an unreliable layer? I do things like wanting acknowledgements for when messages have been received. Good. Now on top of that, I want to build something where I can say, transfer this from here to here for a banking transaction. Okay. What messages are involved in that? I've got to do some authentication, so there's authentication messages in the protocol. There are acknowledgement messages saying, yes, I've done this, you can now complete that transaction this way. So multiple layers of protocols. But doing them formally is a really good idea. I don't mean going and writing some type of abstract syntax for it, but knowing what the message protocols are is an essential part of that component design. And you probably also want to think about the failure modes for those components as well. What happens when a component fails? How do you know it fails? Do you say, do this for me and crickets because it died? What do you do? How does your protocol handle that? Do I retry? Say, I told you to transfer $1 million out of my bank account and I haven't heard. Oh, just go and transfer $1 million out of my bank account again. That's probably not a good response. So later on we'll talk about idempotency. It's a lovely word, which means that you can design these protocols so that you can repeat operations safely. So one answer might be, things fall over, well, we just try again. Knowing that our protocol is smart enough so if it gets a duplicate message, it will safely handle it. Because if you ask me to send you $1 million and I send you the $1 million and I don't hear back, it could be that you've done the transfer, but the acknowledgement got lost. So in that case, if I tell you to do it again, then you can say, I've already got the $1 million, don't worry about it. So you have to think about the failure modes in order to get that idempotency. But we'll talk about that when we talk about availability later and how you design systems. But it comes back to protocols and the behaviour of the components, the failure behaviour of the components. We'll spend a lot of time talking about transactions, which is something I'm very fond of. And Alan and I did a lot of work on transactions. Alan's academic area is transactionist stuff. And they're all about that same question of how do I design something so that I am... If you think about state transitions, and we'll be talking a lot about state. So everything in our system has a state. It's the real world has state. This room has this many people in it. That's the state of this room just now. And there are and then the front row has this many people sitting in these spots. We can just define lots and lots of state about this room. 5 people are asleep, 2 people are really engaged, etc. Lots of possible bits of state we could have about this room. It's state. But for writing really robust systems, we need to care about state transitions and state robustness. So if I'm going from one state to another, are there illegal states that I shouldn't be ever allowed to get into? If I'm moving money from my bank account to your bank account, we might want to have a rule somewhere that says the money can't just go missing. The money either has to be in my bank account or your bank account. It can't just disappear. Now, the bank might like it to do that, but because the money sort of exists somewhere, but there's a rule that says money can't disappear. It all has to add up. And transactions are amongst the tools we use to make sure that type of rule happens. And when we talk about transactional software later on, the importance of that is that it's really, really hard to design software which meets those requirements. Because there are lots of arcane, tricky failure modes, and you have to think about all of them. And you have to be very robust about thinking about the failure modes, all the components, their behaviour, the protocols all have to be designed so that when someone pulls the plug on something, you recover, and you recover into an allowable state. If someone unplugs the cable between the two of us in the middle of that $1 million transfer, things happen, right? And you have to make sure that at the end of it, the money's either in my bank account or yours, and if it's in your bank account, I know it's been transferred, and vice versa. So there are allowable states, and to do that, we use transactions. But we want to be able to do that on systems the scale of Amazon or Azure or something, where we've got geographically distributed data centres around the world, and we've got systems which are integrating things from 100 different organisations, and we still want to guarantee that we have allowable states and we move from one allowable state to another. And that's really hard to do. And there's a lot of infrastructure transactional stuff around about that. And if you think people don't care about that in the real world, they do care about that in the real world. And a lot of the work that Amazon and people were doing when they were designing their systems, was just about consistency and transactions and how you ensure consistency. Because people don't like having money going missing. So, lots of things there. So how do we take overall functionality, chunk it, distribute it? How do we get the bits talking to each other? Multiple layers of protocol, and what are all those responsibilities, including non-functional responsibilities for components? Okay. Now, you want a short break, or you want me to just run through to 8 o'clock? And your call. I'll run through. I can talk for hours. Okay. Communication. Deep down, there are only messages. That's it. I pass a message to you, you send a message to me. That's all there is. But because they can be, and sometimes we just use raw messages. Sometimes we say, that's okay, I could use raw messages, but there's lots of common functionality I want. So we'll use an abstraction above the raw messages to provide some useful things. So who can I pick on? I'll pick on you because you're really awake. So I could ask you to do something and you normally respond, but sometimes you're asleep. Or sometimes you're busy doing something for somebody else. And so if I send you a message, what happens if you're not listening? Because you're not listening, you're asleep, right? You'll wake up in 5 minutes, but if I just sent you a message, and I sent you a TCP message, or an IP message, it's a UDP message, for example, I send you a UDP message, whoomp, and if you're not listening, it'll go whoomp off into the ether and disappear. And here I am waiting for a response from you, and you never saw it because you were asleep. And it's disappeared. So yes, we could use raw messages. We could build this whole system out of UDP and really low-level code, but we then have to worry about how do I handle all those cases. So I said, all right, perhaps I'll use something else like a message infrastructure, a message passing system. So there's a whole layer of stuff we'll be talking about messaging and message passing, perhaps queued messages. So in this case, we'll go back, and a lot of these things we talk about, these ideas are centuries old. You just have to think, it's one of those. So instead of me just throwing a message in a paper plane whoop, in your general direction, you've now got an in tray next to you. So when I want you to do something, I'll walk up and I'll put the message in your in tray, and you take things out of your in tray and process them. And that in tray is a queue. So we could do queued messaging. So I can say, okay, you've got a queue there. I talk to you by dropping a message in a queue. There might be 0 messages in it, 100, it doesn't matter. It's a queue. And then when you're ready, you go and look in the in tray and you can do something for me. So there's a layer of abstraction there, perhaps queued messaging. That may or may not be a convenient programming interface you want to use. You might say, oh look, I'm really a Java programmer and I know how to do method calls, and all I really want to see is method calls. Okay, so we can do another abstraction where you say, you think you're doing a method call, but what you're actually calling is a little bit of stub code, which takes what you did, takes your method call, and turns it into a message and drops it into your in tray. And then when you want to get at it, something magic happens and that message in tray gets turned into a method call and called on your code. So we're putting another layer of abstraction on there to make it easier for the programmer. So we may be making things look like, if it's local, it might be a real function call. We might be trying to hide the fact that this thing we're calling isn't really local, or it may be local sometimes, it might be remote other times, by putting a layer of abstraction in there, in which case we might get function calls that are really remote function calls, or we might actually see messages in their own right. All these things are possible. Some things are harder to do as a program than others, so we might go and build up layers of abstraction there. Control flow. I talked about protocols. That's the first bit, the flow of messages. We'll talk later about parallelism, how we handle things happening in parallel, because we're going to need parallelism for performance. There are really lots of tricky things about synchronization, particularly if you're doing distributed synchronization. How do I know something's been done? I've got a workload, I farm it out, and how do I know when the workload's been completed so I can get back? There are synchronization questions there. So lots of interesting technologies in concurrency control, parallelism, and synchronization. I talked about transactions and how hard real transaction code is. One of the problems that transaction code addresses for you is parallelism. I want to do lots of things in parallel, and I want to do those parallel things on shared state. So how do I handle all the issues that come out there? So transactions help there as well. It's really quite tricky code. Anyone who says, oh, I'll just write this stuff without using some of the infrastructure is probably being very naive. And someone says, I'll just write my own infrastructure to do that, is really being naive. There's decades and decades of work on to achieve these goals. Okay, patterns. So I give you some raw technology and say, hey, go and build something. And you think, well, how do I build this? And what you might want to do is go and find something which is a bit similar and say, I'll base my architecture on this one because it's pretty similar. And that's been that idea of let's take something which is similar and build on it. That's turned into these ideas of patterns. So often the types of things you want, someone has done a lot of work thinking things of this type of thing you can build like this. These are patterns. And the nice thing about patterns is that they've been used successfully in the past for other systems, and people have thought about the problems and there are solutions to them. So patterns are reusable, proven architectural solutions for things. And it also helps communicate as well. If you can say to someone who is aware of these patterns, oh, I'm using the Blogzo pattern for this. They, yes, I know about the Blogzo pattern. It might help communicate designs. But, of course, different parts of your system will be built using different patterns. Those things there, client-server is an architecture. You can find patterns on how to build a client-server system. Message buses. In the spaghetti diagram I had before, it's a spaghetti diagram because it's spaghetti. It's evolved that way. But we used to have a slide or two in this lecture deck on lecture 2 in this slide on this course on messaging and message buses, because that was seen as a great white hope, that we can take all these things and we say we're going to put a single bus, like a electrical bus type thing, and then if you want to talk to the person at the back of the room, there's a connecting bus all the way through. You drop your message on the bus and it travels through and they pick it up off the bus at the end. So we replace all the individual bits of spaghetti with a single communications channel, and that's the message bus model. And then people said, oh, we could write software that will do common things. They give you message broker models. You go to a hub and spoke model with the message broker at the hub. So they're just some architectural patterns that people have developed. And there are lots of books on patterns, and Alan referenced a Microsoft architectural thing which we'll talk about later, and that came out of their group called Patterns and Practices. So they had a group whose sole job was to devise and write recommendations and patterns and good practices. So patterns might save you a lot of time. A key part of architecture are non-functional requirements. Functional requirements are what the system has to do. The non-functional requirements define how well it is going to do it. And that's a key job of an architect, is to think about these non-functional requirements and make sure they're threaded through the very fabric of the solution. There was an email system I was the architect for, and I was really quite pleased with the architecture of that system. And we had several big chunks, and it was an OSI-based model, so we had well-defined chunks for some of them. But the whole architecture of the system, we had two major functional additions to the system while we were developing it. And it coped with it. So the architecture was strong enough that we could say, oh, now we need to add this new thing, and it can plug in here, and we didn't have to tear the thing down. We could say, yep, the architecture is robust enough that we could cope with those changes. And all the way through, you had to think about performance, availability, reliability. So these are all non-functional requirements, but if they're not satisfied, the system may be functional, but it just doesn't work. So Alan said that, I'll give a bit of history of me. So once upon a time I used to work here, Sydney Uni, Computer Science School, and databases, system software, etc. And then I escaped and went and worked in industry. I worked in industry for about 10 years, doing software development, architecture, etc. And then I escaped from there and went and worked with Ian, doing distributed computing research, middleware research for Cyro. And then about 10 years or so ago now, the chief of my division said, would you like to work between biology and computing? And I said, yeah, I'll be a real scientist. So these days I'm a scientist, a real scientist. But it's good because instead of just talking about software, I get to write lots of it. But I write bioinformatics software, and I really, really, really care about performance because I'm dealing with very large data volumes. So for me, those non-functional requirements of does this software work fast enough are really important. It's got to work correctly, but if it's not working fast enough, it's just not useful. So I write pipelines to analyse certain types of data, and they take half an hour to run. People say, that's fantastic. It was taking me 2 weeks on something else. I think, 2 weeks? What type of idiot wrote that? 2 weeks is just not doable. The servers fail every 2 weeks. How do you get things actually complete if you've got to wait weeks? So the type of stuff I do these days, the non-functional requirements are about performance and scalability. The data sets I deal with, you measure in gigabytes. I've got data sets which are, so they're 1.6 billion reads. A read is 100 bases, so that's 1.6 billion times 100 things. And that's the data set I've got to process. And I care about memory space because I really can't afford to use more than half a terabyte of solid memory. And I care about, is this going to take a day to run? Is it going to take half a day? Is it going to take a month? And people write software that takes months to run, and they're non-functional requirements which are really important for practicality. So there are layered architectures, just like in real architecture you have layers. There's the concept drawing. There is the next layer down saying, now this building is built around a steel core of this type of thing, and let's set Opal Tower, that you hope they actually build what you asked for. but you've got layered architectures and more refined designs. So there is no, you can't say, here's the architecture for this. You can have a high-level architecture, you can decompose that, you can refine it. This is a 4+1 view. So these are all architectural descriptions. The logical view, what are the big chunks? How do they relate to each other? The concurrency and communications, what are our protocols? How do the components relate to each other in time? The physical view, how do we physically take the processes and components and deploy them? The development view, so what's it look like? How do I take this architectural thing, and when I'm in a development environment, what's it look like? I might have 20 or 30 bits of software which are being developed in parallel, and how do I do that in a development environment? How do I manage the development process? How do I control it in, say, source code, configuration management here, in the source code questions, and the development environments will help you with those questions. And underlying all that is requirements, the architectural use cases. Some of those are functional use cases, some of them are reflecting those non-functional requirements. What's an architect do? Talk a lot, most likely, and think. I suppose the first job is to understand what it is you're trying to do, which means you're talking with the stakeholders, the people who are defining the functional and non-functional requirements. I can design a system which is highly robust. It can cope with failures. I can give you whatever reliability you want. I can give you really high performance, and there'll be a price tag to go with it. The stakeholders may say, well, that's all well and good, but you can't have $100 million to develop it. You can have $1 million. There's a lovely diagram you've probably all seen, this little triangle. You know, there's something like quality, speed of implementation, and resources. It says, choose two. You can't have all three. So you've got, part of the role of the architect is to how do I balance? I've got this type of resource bucket available, I've got these types of functional requirements, I've got these non-functional requirements. How do I build something which will do the job given the resources I have available? If you had twice the resources, you may be able to do a better job in this part or this part, but you don't have twice the resources. So that basic engineering of coming up with a good solution. Not a perfect solution, but a good solution. And being pragmatic about things. To do that, you really need to understand the technologies you have available. There'll be some lectures I haven't written yet, which will be replacing some of the previous lectures towards the end of the course, where when these slides are fundamentally the ones I did about 10 years ago, and at that stage certain things were important and certain things were me saying this is the way the world is going, and now you say, well, the world has gone that way, those things aren't important anymore, these things are still fundamentally important, and those things we said were the future direction, they've taken off technologically. But you expect that your architect is aware of the technologies available, the technology directions, the technology futures. And one of the reasons that spaghetti diagram was the way it was, there were architectural decisions, technology decisions taken 15 years ago, 20 years ago. And that investment has been made, and no one wants to go and take the risk and put the investment in to undo that decision, because it still works. So you've got to be pragmatic as well as aware of where the world is going. You're responsible for the highest level, you and other people probably, of that high level software engineering, the decomposition, the structure of everything, the way the system is designed. And risk management. Any of you here actually practicing real live software developers? And nothing ever goes wrong, does it? No. Every project you're on comes in under budget and on time, right? Yep. Absolutely. Yes, I keep on trying to tell people it doesn't work that way, but which is something that Alan could have mentioned when you're doing the group project. Remember those lessons that this will only take me a day. Things that take me a day normally take me a week. Things which that's only 5 minutes work and normally an hour. And that's the way it is. So your job as the architect is to be aware of that, and that's factored into the design as well. The two banking projects I'm aware of, one which was the Westpac disaster, which only saved up 100 million. Yeah, so CS90 is the thing they probably never want to mention. And the Combank one, which could have gone just as pear-shaped, but their tech team did a good job, and they were much more constrained. We're just doing the customer system. We're not rebuilding the entire banking system. So constrained, using that constraint as a tool to help you. So I've been involved in projects that we ended up just canning because people were, I'm going to do an OO design, I'm going to do this, I'm going to design some objects, and I don't know what the whole system's going to do yet, but I'm going to spend a year designing a perfect OO model for something. I think, why are you doing this? And after 2 years, the customers run out of patience and we don't have any money. I don't know what happened in Queensland with the health department payroll system that they'd spent 100 million on, and IBM totally destroyed. But there was another not very long ago system that was $100 million of investment and nothing came out of it. And the fault for that would be, lots of people at fault, but some of it would have been the overall architecture of that system and the lack of planning for alternatives, or considering whether if I take this path, these are the possible risks in that versus another lower risk path. So risk management is an important part of that design. These non-functional requirements, sometimes called the ilities, although performance doesn't end in ility, but availability, portability, scalability, reliability, most things end in ility, and performance. You can some performability if you want to call it that. And they're all non-functional requirements, and they determine how well the system achieves its functional requirements. You can have a system that meets the functional requirements and is still effectively useless. And if someone is giving you one of these sort of quality attributes, it's got to be precise enough. So it says, you've got to make it scalable. Well, what the hell does that mean? I don't know. It might be that, we currently want to support 100 concurrent users, but if everything goes well, we might want to support 10,000 concurrent users in a year's time. So when you're designing your architecture, you've got to think, so how do I go from 100 users to 10,000 users? Will my system cope with that? Is there going to be some fundamental bottleneck in the system which needs to be architected around to let me do that type of scalability? If I needed to go to 10,000 users, can I even do that? Do I need to radically change it? It might be that any individual box in my system has a limit of only 1,000 users. So I can scale up, and I'll talk about scaling up and scaling out later. I can scale up only to 1,000 users. At that point, I can't run a single monolithic system anymore, and if my design is built around a single box running the application, I'm stuck. So scalability, so it must be scalable. Yeah, sure, I can double the number of users, but what happens if it's 1,000 or 10,000 times the number of users? So that's a very important specification to get when someone says it has to be scalable. Well, what do you mean by scalable? It's got to be highly available. Yes, what do you mean? Do you mean 99% of the time? Do you mean 99.9% of the time? How do you handle scheduled maintenance? How do you handle if a system falls over? How do you get high availability? So if you get numbers for those things, then you can work out whether the proposed solutions you have are capable of giving you those, fulfilling those non-functional requirements. Performance. We spent a lot of time talking about performance later. Alan's going to give you a lecture on performance modelling. And there are basically two things we measure. Response time. How quickly can my application respond to some request, some event? And how many of those requests or events can we process in a given amount of time? So response time and throughput are the two normal performance metrics we care about. So the non-functional requirements for performance might say, here's what I require. I require 3 seconds is a bit slack. Say 1 second average latency. So I say in there, averages are evil. Averages are a really, really horrible statistic. And I'm getting more and more allergic to the use of averages because they hide sins very, very badly. So, great, we have a 1 second average latency. And if you play, some of you must play video games here, right? How many frames per second do you get in your video game? I get an average of 60 frames per second. How playable is the game if every now and again I get dropped down to 10 frames per second? You're playing it and goes, and it's unplayable. So, but the average might be 60. But that's useless to you. You want an average of 60 with a guarantee that you don't go more than this or this outside of that average. You want to draw a distribution curve of the latencies and make sure that the width of that curve is within some strict limit, because it will be unplayable if you go outside of those limits. So average latency is really evil, so people are now starting to publish more and more information about the distribution of those latencies and put constraints on saying we have to guarantee that the 99th percentile is less than something, so that 99% of all the latencies we observe will be within this constraint. And then you might say 99.9% of them are within some other constraint, depending on what the penalties are for going outside that latency window. And some number of transactions per second. And of course, one of the problems is that all these various constraints impact on each other. So the way I might get really high, really good latency might not also give me really good availability. So these things are not orthogonal. I think I've probably said that. I spent a lot of time with Ian doing these types of curves. And I think these are really misleading as well. I hate these types of curves. They're really common and they are really, really misleading. To me, so we've got the bottom blue curve there is the system CPU utilization. The top curve there is the messages per second number, the throughput. And we've got this lovely, basically, line. If we double the resources, the throughput doubles. Really cool. We're in the sweet part of that scalability curve. And then people say, oh, and then it tails off. It goes asymptotic. And they'd say, oh, this system throughput of the whole system is a maximum of 250. I read that and say, when you got to about 5 threads, you hit some resource bottleneck which stopped you going any further. So to me, everything from 5 onwards is an overloaded system. It is not performing well. And you notice that it drops down at 15, which is an indication we're now getting significant resource contention and queuing. So that's not a system which is working well up at 250. It's a system which is struggling at 250. And if you were to look at the latency distribution curves at each of those points, when we're down here, it'll be a nice tight peak, and the next one will probably be pretty good tight peak as well, and perhaps even 5 will be a good peak, but at 10, I guarantee it'll be a big fat thing, and at 15, it'll be really big. The latency control will be horrible when you get up high, because that's a severely overloaded system. Even though we're only using we're using some fraction of the available percentage of process time. So I look at that and say, that system, you need to investigate why that's tailing off, because systems which are scaling well are not doing that. This is a system which is overloaded once you're past 5 concurrent server threads. And I guarantee there's lots of things it can be. It'll be resource contention of some form or other. Response time's often important. I talked about you want to give constraints on them. And it's really typically an important thing for an end user, because they're waiting. You push the button, and if you haven't got a response in a second or two, you think, that didn't work, I'll do it again, which causes you more problems. And if it's too slow, unless it comes up with a message saying, we're billing your credit card, whatever you do, don't do anything now, because otherwise we'll warn you. Otherwise they'll just, it's too hard, I'll close it, go somewhere else. So it's a critical customer satisfaction metric. But as well, we often build systems that are calling on lots and lots of other components to get, and aggregating it all, and each of those has a latency. And if I'm accessing them all sequentially, the overall latency of the system is the sum of all the individual latencies. So it's very easy to get, that's sub-second, and that's sub-second, hang on, that's sub-2 second now, that's sub-3 second, 4 second. And the classic example of that would be your typical chatty, noisy web page, where it takes, you start seeing it, and then it's busily loading stuff in and loading a megabyte of JavaScript from this library, etc. And it takes you 20 seconds to get the web page up, because of all the individual requests that it's doing. It's not just go to that server, give me a page back. Oh no, the JavaScript is going and fetching stuff from 100 places, and you're seeing the aggregate latency of all of that. Scalability is how your system works when the workload increases. We can talk about what happens with the numbers of requests coming in, increase, the numbers of connections you have to deal with, the size of the data you're dealing with, and a deployment question as well. There are two solutions to scalability. The traditional one a long time ago was scale up. You go to IBM and you'd buy a machine X, which had this much processor power, and you go to them a year later saying, gee, the machine's getting pretty busy. Oh, we've got a model which is twice as fast. There you go. Put the twice as fast one in, pay us another $1 million a year, and you're right. Good. That basically stopped happening about 10 years ago. All processors are now more or less the same speed. And that's just the physics. We can't fix that. You can do binning and say this is a faster chip versus a slower chip. You can pump more power in, but we've basically hit a brick wall due to physics. So now you can't say, oh, I'll just buy a faster machine. It doesn't work. You can buy a machine with more processor cores on it, but now I have to be able to use those, and if I've got a single-threaded application that can only use one processor core, having more processor cores sitting there idle doesn't help me at all, so I have to have an architected solution where I can use those multiple threads, multiple cores. It's an architectural solution. So I can't scale up, I'm really going scale out on a single machine even. And then I say, I can say, let's run it on multiple machines. Cool, I can go scale out that way. So scale up, scale out. Scale up is basically dead. Scale out is the only game in town these days. I can have connectivity, scalability questions. If I've got a web server and I'm getting requests in from over the internet, and each one of them is opening up a connection. Perhaps the connection is semi-permanent, I keep it open for a while, but each one of those connections is a resource and it takes up resources on the system. It's either just memory, or it could be that I have a fixed size table of connections, and when it's full, I can't take any more connections. Often, I might have algorithm problems. I've got a system which scales really well, but I'm doing a linear search on something, which is fine if I've got 10. When I have 1 million, a linear search is just infeasible. So perhaps I need to radically change all my algorithms inside some bit of infrastructure to cope with scalability questions, even for connections. So there's an example there. Perhaps an ISP would be spawning a new process to handle each new connection. That's cool, except that each of these processes used up virtual memory, and the operating system says, you can only have this much virtual memory on this machine. Goes along, and all of a sudden I get to a point where, if I'm really unlucky, the operating system says, I'm sorry, I can't do anything anymore, I'm dead, and it all crashes. The old-fashioned Unix way of doing web servers, you sent an HTTP request in, and it started up a process on that machine to handle your request. And that's just not scalable. It's scalable for a small thing, but if I'm dealing with hundreds of connections, I'm starting up hundreds or thousands of processes per second. No matter how lightweight it is, that's still a big overhead. So lots of questions there. And data size. So I've got an application, that's all cool, and it's all running well, and then all of a sudden I have to deal with 10 times the number of customers, or I have to deal with a 10 times bigger, 100 times bigger database. Now, it might be the database technology, because they really care about scalability as well, say, not a problem. If you'd chosen the right type of indexes and built it all properly for scalability in the first place. But you can get away with things on small systems that when you go to 1 million, you can't get away with anymore. And as an architect, perhaps you need to consider the scalability of the actual code and the infrastructure you're using. Now, it sounds like a really arcane academic question, and there are people over there who care about these types of questions about code performance, but knowing the order of your algorithms is really important. Is this code order 1? So if it works in 1,000 seconds with 1,000 requests, if I give it 10,000 requests, it'll work in 10,000 seconds. It scales linearly with the workload. Or, that's order n. If it's order 1, it just happens. But it could be order n squared, or order n log n, in which case as the workload goes up, it gets exponentially slower. And they sound like really arcane academic questions, and I don't like arcane academic questions, but I care about this in my software all the time, because I'm trying to write things that handles millions or billions of things, and anything when you multiply it by 1 million or 1 billion gets really slow. The piece of code I've been bashing out lately it spends most of its time doing a hash table lookup. And I've optimized that hash table lookup. I've rewritten the code multiple times, and it's an order 1 operation, but I'm doing billions of them.